You have learned a whole stack of techniques, integration techniques, to integrate various functions. But in the grand scheme of all possible functions, it is possible to integrate algebraically a small portion of them. The vast majority of real-world situations give you functions that you cannot integrate with algebra. There's no way to do it. So what we do is numerical integration. It's exactly what your calculator does when you ask it to integrate between 2 points. There are many techniques. Suppose I get, I'll still work over here. Suppose I have some function. That wasn't very clear, was it? Let's make it a bit darker.
Is this the background information that we don't necessarily need to know?
Yeah, I haven't quite got here yet.
Okay.
I'm going to. And I want to find the area between 2 points. The naive thing to do is to divide it up into sections and then go. I'm going to get a rectangle here, and a rectangle here, and a rectangle here, and a rectangle here, and a rectangle. If I add up those rectangles, I'll get an approximation for that area. Except this is too much, and this is missing some. So it's not very accurate. This is the leading rectangle. You take a rectangle from where you first get to that point. Make a rectangle. Okay, sometimes maybe I could take a trailing rectangle. I could work a rectangle out based on where it finished instead. But you know, it's still going to be an approximation. It's still not going to be right. What can I do to get a better approximation?
Simpson's rule.
Before I get to Simpson's rule, there's something simpler.
You could find a line that better fits the rectangle, or
No,
you
I'm
can
just
make the
gonna draw that
rectangle
again.
smaller.
Hang on. Work. Okay, from here to here, what am I going to do?
Make the rectangle smaller?
How?
What do you mean how?
Make it smaller. How do I, what kind of smaller? How do I make it smaller?
In width.
Oh, reduce the width.
Yeah.
Have more. Yes, absolutely.
And you could also use a function instead of a line.
This is where, well, kind of. I don't want to change this though, because that helps me get a straight line and a height. I can calculate an area easily. But see, I'm using a rectangle. Is there a better shape I could use instead of a rectangle?
Trapezium.
Trapezium, right? I can draw a line, a different colour. I can draw a line between those 2 points. It's still not going to be quite right, but it's going to be much better than rectangles, right?
Mm-hmm.
That gives us what you will learn in methods as the trapezoidal rule.
I saw that in the text.
And in methods, you will learn that technique for approximating an integral. But if this is particularly wavy, and for whatever reason I can't make my boxes much skinnier, then I need something more accurate. And Simpson's rule is more accurate. What Simpson's rule does is, it takes every 3 points, and it says, let's make a parabola joining those 3 points. Because any 3 points determines a quadratic, determines a parabola. And then we take the next 3 points and we make another parabola. Obviously for this technique, I need an even number of pieces. I have to have an even number because I do everything in groups of 3 points. This point, and this point, this point, and then I make a parabola, smooth parabola that joins those 3. And Simpson's rule says we can work out at the area of this section down by a parabola, and then we add those sections up. That's what Simpson's rule does. So, Simpson's rule says, can I write this in words? How can I write this in words? partition, not divide, that's a better word. Partition the x-axis region into an even number of intervals is a better word, intervals, and approximate using parabolas. Right? Even number of sections, I only need 2 sections to determine 3 points. So, we're going to take our function, whatever it happens to be, we're going to go from here to here, and we're going to go 1, 2, 3, 4, 5, 6, for example. Here n equals 6, there are 6 sections. This has to be even for this to work. These 3 determine a parabola. The next 3 determine a parabola. The next 3 determine the next parabola. Make sense? That's what Simpson's rule does. Now, if you do this is where the hand waving starts. How do I write this? Suppose I call this A, B, C, D, E, F, G.
Why?
Right? So I want to get the integral from A to G. I want to approximate it. Well, it turns out if we have a parabola here, I can get it. So the integral from C to E, my original function might have been f of x. I'm going to approximate it here with a parabola called p of x. And the integral of little p of x is, as it turns out, I need one more thing to define. This width here is w.
And the width is the same for all of them, right?
The width is fixed for all of them, correct. W on 3 times P of C plus 4P of D plus P of E. I am not going to prove that. It is a question in the coming exercise if you want to try it.
Is that just a formula?
Yes. It says you divide the width by 3, and this formula gives me this area here. Well, the parabola approximation to it. Now we've chosen our points here on the parabola. So these 3 points match my original function. So I'm just going to replace this with f, f, and f. But then watch what happens. I'm going to add 1 here, and 4 here, and 1 here. That gives me this area.
What do you mean you can add 1, 4, and 1?
1, 4, and 1. 1 of this, 4 of this, 1 of this.
Just a formula?
It's coming. Right, see the next one has something with 1 coefficient, something with 4, and something with 2. Can you see that?
Yeah.
I'm going to show you where those numbers come from. Right? 1, 4, 1. Again, I'm not going to try and prove, I can prove this, but I don't want to until you've actually tried using the rule. So 1, 4, 1. But then the next section, I'm going to have 1, 4, 1. And then the last section here, 1, 4, 1. So each of the points in between, the even points in between, I'm actually going to get 2 of. If I add these up, there's 1 here, 4, 2, 4, 2, 4, 1.
Mm-hmm.
Which is why this formula has, I'm going to write it for you in a different order. 1, 4, and 2 terms, and then 1 again at the end. I'm going to write those terms in a different order. In this case, I'm going to get the thing I actually want, a to g of f of x, is approximately one lot of f at a plus 4 f at b plus 2 f at c plus 4 f at d plus 2 f at e plus 4 f at f. Well, that was confusing.
Are these points or parabolas?
These are ABCD are x values, and you are evaluating your original function at those points. I'll show you an example in a second. I just want to show you where the numbers in the formula come from.
Okay.
Oh, I've forgotten something. Hold on. W on 3 times plus 1 lot of f at g. So it's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 1 at the end. Why is it like that? Because this formula tells you for each section, each pair. And then the points that, each of the intermediate points, you add 1 on the left and 1 on the right. 1 on the left and 1 on the right. That's why you always get 2 of them.
Right.
Let me show you how we actually do this in practice. Use Simpson's rule with n equals 6 sub-intervals to approximate. Right, let's go. E.g., use Simpson's rule with n equals 6 subsections. No, sub-intervals. Use the right word. That was a bit messy. Intervals to approximate the integral from 1 to 2.2 of 1 over x dx to 3 decimal places. So this is 1, this is 2.2. We're going to work at all the points in between to get our 6 intervals. That's also going to give us our w.
What's the point of the 1 on x?
Sorry?
What's the point of the 1 on x?
Well, this is the function I want to find the integral of.
Right.
What's n? 6. Oh, there's 6 points. Yeah.
6 intervals. 6 intervals, which is actually 7 points.
Okay.
Okay? There are 6. There always has to be an even number in the intervals. So, this is what we're going to do. Our f of x here is 1 over x. That's the function I want to integrate. My width is, how far is it between 1 and 2.2?
1.2.
Divided by 6 intervals. And then we make ourselves a nice table. X, which one are they doing? Yes, that's right. F of x multiplier total. And we're going to go 1, 1.2, 1.4, 1.6, and we should have 7 points because I've got 6 intervals. Draw up your table. On the exam, even if you use your calculator, your graphics calculator, still write up the table. So if you make an error somewhere, your working is clear, we can see where you made it, it's just one simple mistake, and you won't lose too many marks. We can see what you did wrong. I can already fill in the multiply column. It goes 1, 4, 2, 4, 2, 4, 1.
Is this just something you have to memorize?
Yes. Well, I mean, the numbers are on here. It's just not very clear from this formula.
That's okay. It's
one lot of 0 and n,
Yeah.
4 lots of all the odd ones, and 2 lots of all the even ones.
Right.
Whereas I think of it as going, it's easier for me to go 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1.
Damn, how many 2 4s do you
On an exam, it's going to be 4 or 6 intervals because anything else is just a waste of time. We need to see you know the technique. We don't need to see that you can apply it with 20 intervals.
Is it always symmetrical?
Yes.
Okay.
Because it comes from this.
Yeah.
So it's always going to be symmetrical.
Yeah.
There's always going to be a 4 in the middle.
Mm-hmm. Does the textbook do it like this or do it like the syllabus?
Draw the table. See?
Yeah.
There's your table.
Yeah.
Okay. What is 1 over 1?
1.
What is 1 over 1.2? Calculator time. Which calculator out? Which calculator then?
0.8, I'm guessing.
Which calculator then?
Already. Five on 7.
How's that possible?
7 on 5.
Because this is 7 on 5. I want a decimal.
Oh, my bad. I had
My
some-
answer has to be 3 decimal places, so give it to me in at least 4 decimal places. What have we got?
0.8333.
Yeah, I wasn't far off.
Okay. 1 over 1.4 is?
.714.
4 decimal places.
Oh, you want 4 decimal? 0.7143.
I want 4 decimal places here because I want to finish with 3.
Right. Okay.
Intermediate with more than you need at the end.
Okay.
1 over 1.6 is?
0.625.
0.
Okay. 1 over 1.8. Other Ben?
Calculator still loading. 0.5555.
Go 6 at the end.
So I'm going to round up to 6, right? 1 over 2.0, that's easy. 1 over 2.2.
0.4545.
Totals, multiply them. I could probably do some of these. Times by 2, 1.428. I don't know what the last digit is. Is it a 6?
Wait, are you just
Or
like
7?
progressively adding them together?
This times this is this. 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 At the end, I'm going to go total equals sum of.
And this is like the fastest way to do it?
No.
Oh.
I'm glad you asked.
Okay.
But I want you to see what the system is doing. We'll do it once like this. Then I'll show you how you can use your calculator to make it quicker.
3.3332. Next one up.
It was the one above it.
One above
The
it.
1.2.
This?
Yeah.
Oh, because times 4. 3.3.
332.
Okay. I need to know the last digit of this one.
It's 6.
It is a 6. Oh, you just
2.5.
type this number in and times it by 2. Yes, it will be. But if you still have 1 over 1.4 times 2, what do you get? We're losing some precision here. Probably still close enough. Let's see what happens. Okay. Times 4 then is 2.48.
5.
5 exactly?
Yeah.
Okay.
1.1112. 5 times 4, so.
Oh, that's hard. Add all those up for me.
Wow. 1 plus. Someone read them out.
8.
What is it?
Well, I did my one, but like I rounded to the second.
Okay. Well, we'll see how we get. 11 point something.
8.2 for me, but
I need 2 more decimal places.
I got 11.8275. What did you get?
Pretty sure that's where you're all.
No, it could be a 5 at the end.
No, not the added together, like the answer.
That's not the right answer, correct.
That's not the right answer.
The single most common mistake
Oh, W over 3?
is W over 3. Forgetting the W over 3. Okay?
So we did all that wrong?
No.
Oh, okay.
The integral from 1 to 2.2 of 1 over x dx is approximately, what's my width?
0.2.
Yeah.
So that's 0.2 over 3 times 11.8275.
0.788.
Yeah, that's what it is.
7?
8.
8, 8,
Exactly?
4, but it's 8, 8. You said
Oh yeah, 3 different ones, correct. Yeah, this is definitely wrong. But that's where a lot of people stop on the exam because you've done all this work and you've got a total. No, you're not finished yet. Simpson's rule says W on 3 times that number. How can we check our answer?
Well, you can integrate 1 over x.
Correct. Right? To check. What is the integral of 1 to 2.2 of 1 over x dx? Well, that is, what's the integral of 1 over x, please?
ln 2.2 minus 2.
ln, what did somebody say? ln x. Oops. 1, 2.2. We'll write every step because you're still learning. ln 2.2 minus ln 1. Well, that's
0.
good. Log 2.2 according to your calculator is?
0.788.
Is it?
Yeah.
Is it?
Yes.
Have you actually checked it?
Yes.
So Simpson's rule got us pretty close. As it turns out, I think it's 0.00005 different. So it's a pretty good approximation.
Right.
There are many situations where you can't do this. We have no algebraic integral. We just have to rely on numerical methods.